In this lesson, we're going to talk about some physical applications of integration. We're going to focus on mass and density and force and work. The first thing we're going to look at is mass and density of a one-dimensional object. And really what we're looking at is a rod or a wire that's thin enough that we can call it one-dimensional. So we're going to use integration to develop a formula for calculating mass based on a density function. And we label the density function here as this notation. Now, this Greek letter that looks like a calligraphy P, that is called the Greek letter rho. And this is the function that's going to define the density at a specific point x. So this is a fixed variable density. Now, if the density is constant, then you're just going to take the length of the rod or the wire and multiply it by that constant density. That's right here. But if it changes from point to point, we have a function that is defined by that point x. So what we're going to do, just like in previous applications, we're going to break up this rod or this wire in small pieces. And the pieces are going to be small enough so that at that point, we can say that it's approximately constant. That density is approximately constant on that piece because we're making those pieces small enough. Then what we're going to do is we're going to add up all those pieces, and the more and more pieces that we take, that's our n, okay? As n approaches infinity, it gets more and more accurate, just like when we were looking at the area under a graph or the volume of a solid when it's rotated around the x or the y axis. We're taking pieces that are so small and we're adding them up that we're going to get a really accurate result. Now, when we take the limit as n goes to infinity, we can use integration. So, to find the mass of a one-dimensional object, what you're going to do is you're just going to put the length of that rod or that wire from A to B, those are your endpoints, and you're going to integrate your density function. Okay, so here's the official theorem. That's right here. And let's look at our first example. So it says, consider a thin rod orientated on the x-axis over this interval pi over 2 to pi. So this is our interval a to b. That's what our integration limits are going to be. If the density of the rod is given by, so here is our density function, rho is sine of x, what is the mass of the rod? So this is a variable density. We're going to integrate from pi over 2 to pi. Here's our rho function, our density function. And when we integrate that, we're going to get 1. Okay, in the next concept, we're going to talk about the mass density formula of a circular object. And we are going to be finding the mass of a two-dimensional disk of radius r. Now, we're going to picture a disk that's thin enough that we can assume that it's 2 dimensions. Rho, or our density function, is now, because we're looking at it in terms of a disk, we call that our radial density. And this means that the density is going to vary along the radius. So if I plug in a value for x here, that tells me how far out to come in terms of the radius. So if I plug in a value and it tells me, I say x is 3 and I come out a radius of 3, that's going to tell me what the density is along that radius. So now what we're going to do to find the mass density formula for a disk, we are basically going to be creating washers, just like we did with cylindrical shells when we were finding the volume of a solid. We're finding cylindrical shells, but we're doing it two-dimensionally, so we're looking at it in terms of a washer, okay? And we're going to find smaller and smaller intervals for that washer from here to here, and we're going to find the area of those washers and add them all up. And the closer we get, or the smaller that change in x is going to be as n approaches infinity, where n is the number of washers, as we create more and more of them and that delta x gets smaller and smaller, we get a more accurate value. So we're going to be finding washers. So this washer, then the next washer, then the next washer. We're basically layering them, and we want to find the washers, the area of the washers as they get thinner and thinner and thinner. So when we set up that formula, the area of the washer is going to be 2 pi, and then this is going to be the radius. So we tell it to how far to come out, 2 pi r, and then we're going to multiply that by our density function, and then we're going to multiply it by the thickness, this thickness here. So we're finding the circumference of that value, and then we're multiplying it by the thickness. And then when we take the limit as n goes to infinity, we get our integral. So we're going to go from 0 to r, which is the radius, 2 pi, we're going to put in our value of x, how far we want to come out from the center, times the density. Okay, so here's our official theorem here with everything laid out. Let's look at our example. Let the density function be equal to the square root of x, and it's going to represent the radial density of a disk. We want to calculate the mass of a disk of radius 4. So the radius is going to be 4, so we're going to go from 0 to 4. Using our formula here, we're going to do 2 pi x, and then we're going to plug in our density function, which is the square root of x, and then of course add in our dx. And when we integrate that, I'll let you work out the details, but when you integrate that, you should get 128 pi over 5. And of course, you can put that in decimal format as well. Next concept in our lesson, we're going to talk about work done by a force. Now, intuitively, when we think of work done by a force, we imagine like a push or pull on a chair. And that's kind of what we think about intuitively, but really when you do work, it's really just the energy that it takes to move an object. That's really what we're talking about here. Now, just like density, force can change or it can be constant. If it's constant, if force is constant, then the work is just the force times the distance. So that's here. If we have a constant force, then work is just the force times the distance. However, if the force is variable and we have some function that defines the force at a given point, then what we want to do is we want to use integration, because we want to find over these small distances, we multiply it by the force. So we want to find the intervals that are so small that when we look at the force over that interval, it's approximately constant. And then when we multiply it by that width of the rectangles, that's multiplying it by little pieces of the full distance. So, and then when we add them up, we get the force times the distance over the entire interval. So what we're basically doing is we're breaking up, when we have a variable force and we want to find the work, we're finding the integral of that function of force from the interval from A to B. Now, depending on the situation, you could have different forces. So when we're dealing with springs, we're going to use Hooke's law, where the force is going to be defined as a constant k times x. And x is going to be how far it comes out from equilibrium. So if this is an equilibrium, if I stretch the spring out this way, then my distance for x is going to be whatever this distance is from here to here, which would be positive because I'm coming out this way with a stretch. If I'm compressing it, then I'm going this way, and the distance that I move from here to here is going to be x, but it will be negative. Now, our constant K tells us basically the strength of the spring. So this K is going to increase as the spring gets more and more stronger. So this K is going to be directly proportional to the strength of this spring. So when I want to find work on an object, I'm basically just taking the function of the force. I'm basically just integrating the force from the interval a to b, wherever it's moving from the starting point to the finish point. So just a quick refresher in the units that we use for work and force. When we're working within the English system, the unit for force is going to be the pound. And when we use distance, that's going to be feet. So for work, when I'm trying to find the unit for work, if force is pounds and distance is going to be feet, then when we multiply that, the unit for work is going to be the foot-pound. Then when we're talking about the metric system, force is going to be measured in newtons, and the distance will typically be measured in meters. So when we multiply that together to find the unit for work, that's going to be a Newton meter. And a Newton meter can also be written as a joule. If we look down here, I wrote a quick review of that down here. So if you want to copy it down, go for it. But let's jump into an example. So in this example, we're going to find the work required to stretch or compress a spring. Now remember, to find work, if it's a variable force, you're going to integrate over the interval in which this object is moving. And because we're talking about a spring, we're going to use this formula for the force. Suppose it takes a force of 10 newtons in the negative direction to compress a spring 0.2 meters from the equilibrium position. How much work is done to stretch the spring 0.5 meters from the equilibrium position? So the first part of this example is giving us enough information so that we can figure out a formula for the force. Then we're going to use that to answer the question, how much work is done to stretch the spring 0.5 meters from the equilibrium position. So the first part gives us enough information to figure out our formula for our force. And we're using Hooke's law because we're talking about springs. So when the force is 10 newtons in the negative direction, so that's negative 10 newtons, and we compress a spring 0.2 meters from the equilibrium position, when we compress, that means the distance that we compress is going to be negative because we're pushing it this way to the left. So the spring is compressed. That means the distance it's moving is negative 0.20 meters. So we're going to use this information here to find our value of K to come up for a formula for our force. So we know that the force is negative 10 newtons. So I put that in for my force. I know my X is the distance that it moved, which is negative 0.2. And we can use that to find our spring constant to come up with our force formula. So when we solve this formula, I'm going to get that our spring constant is 50, which means our force for this spring is 50x. Now we can use our force function to integrate. We want to see how much work is done to stretch the spring 0.5 meters from the equilibrium position. Well, how do I know if I use 0.5 or negative 0.5? This is saying we're stretching the spring, which means we're coming out this way, so it should be positive. So I'm going to go from 0 to 0.5 because we're going from an equilibrium position to stretching it out to 0.5 meters away from the equilibrium position. And I'm going to integrate my force that I found, which is 50x, over 0 to 0.5. And when I do that, I get 6.25, and work should be, because we're dealing with newtons and meters here, I can either write this as the Newton meter, that's the unit for work, or it's the same thing as 1 joule. 1 Newton meter is equivalent to 1 joule. So I can write it as joules or a Newton meter here. So we looked at, in terms of work, we looked at finding work in general, and then we looked at a specific example of finding work done by a spring. Now, our next example for work is going to be finding the work when we pump water out of a tank. Now, when we pump water out of a tank, these are going to be a little bit more tricky because the calculations are going to depend on the shape and the size of the tank. So there isn't really a general formula of just plugging in. We have to look at the shape and the size of the tank and figure it out from there. And the other thing we have to think about is that when we are looking at pumping problems, to find the force, we're looking at the force required to lift the water to the top of the tank, which is basically the force required to overcome gravity. So it's going to be equal to the weight of the water. Now, when we're using the metric system, the weight density of the water we're going to use as this. When we're working in the English system, we're going to use this value here for the weight density of the water. And another thing that we have to consider that's important is when we're doing pumping problems, because we're pulling the water out this way, we want to think of the downward direction as positive, because that's basically what we're going to be doing consistently. So if I imagine that this is my x-axis here, going down is going to be positive in these cases. So from here to here is going to be a distance of positive 2. So a distance from here to here when you're halfway down is going to be positive 5. So just think when you're going down, when you're dealing with pumping problems, those are going to be positive values. So when we look at the shape of this specific tank and I look at a cross section, it's going to be a disc. So to find the volume of one of our slices, it's going to be the area of a circle, which is pi r squared. And it says the radius in this case is 4. So pi r squared, that's my area. And then I multiply it by the thickness of the disk, which is delta x, right? That's this thickness here. And then to find the force, I have to then multiply it. This is a multiplication, not an x. I then have to multiply it by 9,800. Since we're using the metric system here in meters, I want to use the 9,800. So this is going to be my force. Then I have to multiply it. Remember, work is force times distance. So if I want to find the force that's going to lift just this one partition, just this one slice, I have to then move it the distance. So the distance we're calling x, that it's going to be moved. So when I add in an x over here to find my work for moving just this piece here, just this slice here, that's going to be work is equal to 9,800 times pi 4 squared, which is 16, times my delta x, and then times x, which is the distance that it's going to move. So that's going to give me the work for each individual slice. Now, when I partition this into smaller and smaller slices and I add it up over that interval, then that's where I'm going to integrate. So after doing a little bit of cleaning up, I have 9,800. This is going to give me 16 pi. And then this is the x, the distance that each of these pieces are going to move. And then, of course, the delta x is my dx. And the interval that we partition that we're looking at is from 2 to 10. So if this is x is equal to 0 and going down is positive, my interval that I partitioned is this bit of water here, that's going to be from 2 to 10. So that's why this interval here is from 2 to 10 for my integration limits. So now, here I copied this out of the book. It's a problem-solving strategy list here that you can use as a reference. But just keep in mind that generally what you want to do is you want to find the force by taking one of these two numbers and multiplying it by the volume of your slice. And then you want to multiply it by x to get your work for just that one slice. And then you add it up by integrating over the interval that you're partitioning. Okay, so looking at this example here, in this example, we have a pumping problem with an inverted cone. It says here that the height of the cone is 12. So all this information is shown in the diagram here. So the whole height of the cone is 12. The base radius is 4. So from here to here is 4 feet. The tank is full to start with, and the water is pumped over the upper edge of the tank until the height of the water remaining in the tank is 4 feet. So we want 4 feet to be left, which means if we start here, we want to partition the interval from 0 to 8. We want to go from 0 to 8. We want to stop at 8, so there's 4 feet left. Okay, now it's asking how much work is required to pump out that amount of water. So remember what we have to do. We have to find the work for each slice, which in order to do that, we need to find the force for each slice, which in order to do that, we need to find the volume for each slice. Now, in order to find the volume of each slice, unfortunately, as you change and you come down this cone, different distances down this cone, the radius is going to be different. So the radius itself is going to be a function. It's not a constant value. So we need to find the radius in terms of x. And in order to do that, what I did is I used similar triangles. So I set up 4 is to r as 12 is to 12 minus x. So I set up the similar triangle and solve for r. So now we have what the radius is when the depth is x, starting from the top down, when the distance is x, this will be the radius. So to find the volume of our slice then, since our slice is a disk, we're going to do pi r squared. So here's pi. Our radius is 4 minus x to the third, or 4 minus x over 3, and we're going to square that. And then to get the thickness of the slice, we use our delta x. So here's the volume of our slice. And then to find the work for one slice, we have to find either use 9800 or the 62.4 value. And multiply it by the volume and then times x, which is the distance it needs to move. Now, because in this case we're using feet, we're going to use the English system units, which is the 62.4, and then we multiply it by the volume and then times x, which is the distance it's going to move for that slice. And then when we integrate that over the interval that we partitioned, which is from 0 to 8, we get that it's 33,456.7, and because we're using the English system, the work is going to be foot-pounds for the units. So these pumping problems are a little bit more tricky because there isn't a specific formula. You have to really look at the shape of your tank and use that to figure out the volume of each of your slices.